We proceed by analyzing the performance of the thresholding algorithm. As you will see, the path we take is very similar to the one taken for the OMP study. Here again, we rely on the simplifying assumption that the true representation has all its non-zeros in the first S locations, and these are organized in a descending absolute value. When could we declare that the thresholding algorithm succeeds? This takes place when the inner product of B by the true atoms leads to dominant values when compared to the rest of the inner products. Put formally, the minimal absolute inner product with the true atoms should be bigger than the maximal absolute inner product with the wrong ones. As before, we will take these two expressions and replace them with bounds that are simpler to handle. At least when it comes to the right-hand side expression, the derivation is the very same one we had for the OMP. We upper bound this expression by pushing the absolute value into the summation and replacing the atoms' inner products by the mutual coherence. The new expression is simply mu times S times the maximal non-zero in the solution. This is the very same expression we got when analyzing the OMP. Moving to the left-hand side expression, treating it is a bit more delicate. Remember, our goal is to lower bound it in the same spirit as done for the OMP. We start by plugging in the identity of B as a weighted sum of the atoms in the support. In the resulting summation, T equals I implies that an inner product is between an atom and itself, which is simply 1. We move this element outside of the summation, being simply xi. Relying on the reverse triangle inequality, we get that the left-hand side is lower bounded by the minimum over this difference. We can further lower bound this difference by applying a minimum over the first term and a maximum over the other. We are nearly done. Here's what we got so far. The obvious next step is to replace the first term by the smallest absolute non-zero in X, referred to as X mean. We proceed by replacing the atom's inner products by the mutual coherence. Due to the negative sign before of this summation, maximizing it amounts to minimizing the overall expression as required. Observe that we have also replaced all the coefficient absolute xt by the maximal one, again following the same reasoning. The final result is very simple and resembles expressions we have already seen with one difference. Both x mean and x max participate in it, something that will return to haunt us later on. The final stage in our analysis of the thresholding algorithm is to compare the two bounds and get a condition on S for this method's success. Here is what we got. Dividing by x max, we get this, which can be further simplified to lead to this condition on S. It should be smaller than 1/2 of 1 plus 1 over mu times the ratio between the minimal and the maximal values in X. The good news are that this is it. Under this condition, the thresholding algorithm is guaranteed to thrive. The bad news are that this condition has a new ingredient in it that seems to weaken the overall result. And here is this result summarized as a theorem. The thresholding algorithm will produce the exact sparsest solution of P0 if this solution is sparse enough, following this condition that we have just seen. Let's have a closer look at the required S by comparing the two conditions we got, one for the OMP and the other for the thresholding. Clearly, the thresholding condition is weaker compared to the OMP because the bound for success is necessarily lower. Furthermore, this bound exposes a sensitivity of the thresholding algorithms to the contrast in the unknown. The question we must ask is whether this is a true sensitivity or an artifact of our proof. In order to answer this, let's experiment with the thresholding and explore its behavior under varying such contrasts. So following the very same experiment structure as done before, we test the OMP and the thresholding. Our matrix A is of size 50 by 100, just as before. We create random sparse solutions with a fixed cardinality of either 5 or 10, and modify this vector contrast by drawing the non-zeros at random from this distribution. When C equals 1, we get the worst contrast, and when C goes up all the way to 20, we get the most favorable one. Per each such C value, we run 1,000 experiments and test the resulting solution x hat versus the original x naught. And here are the results corresponding to S equals 5, given in terms of the L2 error of the estimate x hat. While the OMP seems to be indifferent to the value of C, the performance of the thresholding algorithm heavily depends on it, just as theoretically predicted. Going to a higher cardinality, where OMP is also challenged, we see an interesting behavior. First, clearly thresholding is performing very poorly across the contrast values, with a slight tendency to improve when the contrast gets smaller. OMP, on the other hand, seems to perform better for high contrast, which is the complete opposite to the thresholding behavior.